Hey everybody, I hope you're all having a great long weekend. So for this week's content, we're going to be talking about radicals and radical equations and how we work with those. So before we get started, just a quick review of what you might have seen in the past about radicals. Things like turning mixed radicals into entire radicals and entire radicals back into mixed radicals. Now, it says put your hands up. Obviously, I can't see you, so please don't put your hand up. This would have been notes I would have done in class. But the idea of converting radicals. So think back to NRF 10 when you were given a question like this and it asked you to turn it into an entire radical. So what an entire radical looks like is it looks like a all the numbers are underneath the radical symbol. So to convert 7 root 2 into an entire radical, what we want to do is we want to take that 7 and get it inside my radical symbol. So in order to do that, we can't just say, okay, well, I can move the 7 inside, right? We can't just say, okay, well, if I take that 7, I move it inside, we get the square root of 7 times 2. It doesn't quite work like that because what ends up happening is in order to move that root 7 inside, we need it to also be under a radical. So what number that if we put it under a square root would be equivalent to 7? It's the square root of 49, not the square root of 7, right? The square root of 49 is equal to 7. So the square root of 49 and the square root of 2, now, yeah, that 49 can come underneath my radical, and this thing, square root 7 root 2, written as an entire radical, is the square root of 49 times 2, which is 98. Okay. And the other way, going the other direction, so for example, if I had the square root of 200 and I asked you to write it as a mixed radical, what I'm asking you to do is to write it as a two-piece thing where part of it is outside the radical and the other part is still underneath the radical. So what we can do for these questions is take 200 and break it up into the largest perfect square we can. So for example, the square root of 200 is equal to the square root of 100 times 2. And again, what ends up happening here is we can't just take that 100 out and say we're going to have, okay, well, it's 100, and then inside we're left with 2. What we're going to do is when that 100 comes out, we have to take its square root. So the square root of 100 is 10, and then we're left with the 2 on the inside. So the square root of 200 is equal to 10 root 2. That would be going from an entire radical to a mixed radical, and then 10 root 2 is also, if we went backwards, equal to 200, square root of 200, and that's an entire radical. These mixed radicals are the things you'll see most often, so really start getting used to seeing this and working with these. Okay, so before we get started, just think about variables for a second. If I were to give you a question that contained both x's and y's, can you add those? So, for example, if I said x plus y, and I gave you that expression, can that be simplified? And the answer to that is no, right? You can't add x's and y's. It'd be like saying 2 squares plus 3 circles is 5 something, right? It doesn't really work like that. So when we have different variables, we can't add them. But same thing is true for radicals. So much like variables, radicals can only be added when they look the same. So what I mean by that is if instead of x plus y, I had x plus x, well, yeah, that thing can be simplified because we have 2x. Well, the same thing is true for radicals. If I have root 2 plus root 2, well, that's just 2 root 2 because we have two of them. But if I have root 2 plus root 3, root 2 and root 3 are not the same thing as 2 and 3, so they don't follow the same rules. We can't just say root 2 plus root 3 is equal to root 5 because it is not. That is not allowed. You cannot do that. For the same reason that x plus y is not equal to 2x or 2y, right? Because they are different things that cannot be added. But when we're multiplying x's and y's, so also like unlike radicals, sorry, also like variables, unlike radicals, can be multiplied. So for example, if I had x times y, that thing can be simplified to xy. Well, the same thing is true for radicals. If I have root 2 multiplied by root 3, now, yes, I can multiply and I get root 6. And the reason for that is that a radical and a exponent work very similarly. They're kind of the same thing, just the forwards and backwards of each other. And an exponent is just a repeated multiplication. So exponents are groups of multiplication. So with that in mind, right, we can multiply two exponents and work with that, or multiply two radicals and work with that in kind of a way that we would be used to. So let's take a look at a couple of these types of questions. So let's try to simplify this. So if I have 2 root 7 plus 13 root 7, because these are both root 7s, we can add these. We can say, okay, well, 2 root 7, so that's two groups of root 7, and then another 13 groups of root 7. So altogether, I would have 15 groups of root 7. Still root 7. We don't add the 7s and get 14 or anything like that. We just have 2 root 7s plus 13 root 7s is 15 root 7s. All right, part B here. So these look like they aren't the same radical, but this is why at the first of the video I talked about going from mixed radicals to entire radicals and vice versa. Because if I took this 24 and I turned it into a mixed radical, well, 24 is 6 times 4, right? So that means 24. If I take the 6 times 4 and I get the 4 out of my radical, it becomes a 2. So this thing turns into 2 root 6 minus root 6. So if I have 2 root 6's and I subtract 1 root 6, I'm left with root 6. Okay, and then the same thing here. Variables will work exactly the same way as numbers, right? In the sense that if I have the square root of x and the square root of x, as long as they are the same, we can still add the numbers that are in front. So, for example, I'm going to simplify this root 20 to give me 2 root 5x, because the square root of 20 is the square root of 4 times 5, and the square root of 4 is where I get this 2 from, minus 3 times, and do the same thing here, 45 is 9 times 5, so the square root of 9 is 3, and again, I'm left with root 5x. So now I've got two groups of root 5x, and I've got 9 groups of root 5x, so 2 minus 9 is negative 7 root 5x. And you'll notice here this symbol here says that x has to be greater than or equal to 0. And the reason that that is there is, again, we think about things that aren't allowed to happen in math. If x were less than 0, these numbers under my radical symbols would be negative, and we know we're not allowed to take the square root of negative numbers, so that's why that's there. Okay, a couple more examples here. So again, this time we're multiplying. So if I want to simplify these things, right, we can multiply radicals easy enough. So root 3 root 6 gives me 5 root 18, right? For this one here, where we can't add or subtract root 2's and root 3's, what we can do, though, is we can take this term that's out front and multiply it into both terms inside my bracket. So negative 2 times 4 is negative 8. And then the cube root of 11 times the cube root of 2 is the cube root of 22. And then negative 2 times negative 3 is positive 6. And cube root of 11 times the cube root of 3 is the cube root of 33. Okay. Radicals will work exactly the same way as exponents or as variables and numbers. If we're multiplying something like this, so something like this, we're going to have to FOIL, right? Because we have a binomial multiplied by a binomial, so we have to make sure we multiply everything. So we got to take the 4 root 2 and multiply it by root 7. So 4 root 2 times root 7 is 4 root 14. 4 root 2 times negative 5 root 14. So negative 4 times 5 is 20. And then 2 times 14 is 28. And then the 3 times root 7, so plus 3 root 7. And 3 times negative 5 root 12 is negative, root 14, negative 15 root 14. So now at this point, what we need to do is make sure that we are simplifying everything that can be simplified. And what I mean by that is, well, we have 4 root 14 here, and negative 15 root 14. Since they're the same radical, we can do that subtraction. 4 minus 15 is negative 11. Sorry, negative 11 root 14. Now these two are still left over, but 28 can be broken up into 4 times 7, and 4 is a perfect square. So this thing can actually be simplified. So 20 times 2 root 7 plus 3 root 7. So now we can simplify even further. So this is negative 11 root 14. And then 20 times 2 is 40. So negative 40 plus 3 is negative 37 root 7. Okay. And then finally, if we take a look at part D here, down a little bit so I have a little more to work with. So D, negative 2 root 11c multiplied by 4 root 2c cubed minus 3 root 3. And again, we're going to say c can't be negative because if it were negative, it's going to make this negative and it's going to make that negative, which we know is an issue when we're taking the square root of negative numbers. So again, what I can do here is I can take this thing that's out front and multiply it into my bracket. So negative 2 times 4 is negative 8. And 11c times 2c cubed is the square root of 22c to the 4 minus, sorry. Now we're going to take this and multiply it in here as well. So negative 2 times negative 3 is positive 6. And then 11c multiplied by 3 is the square root of 33c. So again, this question says make sure that you are simplifying wherever possible. And what we can do here is we can take the square root of c to the fourth. So whenever we have something underneath our radical that has an answer, we're going to take the square root of it. So the square root of c to the fourth is c squared. So this is negative 8c squared root 22 plus 6 root 33c. Okay, so just a couple of examples for adding, subtracting, and multiplying. Now, dividing is a little different. The reason dividing is a little different because we have to be careful of not just making our square roots and things positive, but also making sure that our denominator is not 0. So when dividing radicals, we divide the coefficient and then the radicand. So the radicand is the number that is inside my radical, and the coefficient is the number that's in front. You can only divide radicals that have the same index, so the same little number inside that radical symbol. And the same thing is true for multiplication as well, right? We can only multiply radicals that have the same index. For example, this was cube root, cube root, cube root. Perfect. They're all threes, so we can do that multiplication. But for question C here, if this were, say, cubed root, well, we can't do the cube root of 2 times the square root of 7, right? It doesn't, again, that's your x's and y's, right? So we can't deal with it like that. So here's our general statement. So some coefficient m times the kth root of a divided some coefficient n times the kth root of b will be equal to, so the m and the n kind of get separated. So it's going to be m divided by n. It's going to be a kth root still. The index is going to be the same, but then the radicand are a and b. And then what this second part is saying is that k has to be a natural number, so we can't have like the half root, right? Doesn't make sense. It has to be a natural number. M, N, A, and B are all real numbers. They could be positive, negative, they could be fractions, decimals, whatever. The only restriction is N cannot be 0 and B cannot be 0 because then we'd have a fraction that would have a 0 in the denominator. And if k is even, so if it's a 2, a 4, a 6, whatever the case may be, then we know that we can't take the root of a negative number. So a and b would have to be positive in that case. So lots of restrictions going on here, but the takeaway is that when you do this, you can kind of separate the coefficients from the radicals and do the divisions separately. Okay, so rationalizing. So this is something that you're going to be doing. So you're going to be doing it now. You're going to be doing it if you decide to go on and do pre-calc 12. Rationalizing is a kind of a mathematical thing that we do whenever we have a radical in the denominator. Because in math, we don't like radicals in denominators. We want them to be in the numerators if we have to have them. So what we go through a series of steps that we can take a radical from a denominator and move it to the numerator, and we call that rationalizing. So to simplify a fraction that has a radical in the denominator, we need to rationalize the denominator. And there's going to be a couple of ways of doing that depending on what our denominator looks like. So we rationalize the denominator by multiplying the fraction by something equivalent. And what I mean by that is whatever we multiply the fraction by, so if we're going to multiply it by 23, we want to make sure that we're not changing the value of our fraction. So if we're going to multiply it by 23, then we'd also have to multiply it by 23 in the denominator because 23 divided by 23 is equal to 1. And multiplying anything by 1 doesn't change its value. So what we're doing is we're just going to change the way it looks without changing what it equals. So for example, if I had a question like this where I had 5 over 2 root 3 and I wanted to rationalize this thing, what I want to do is I want to multiply this thing by something that's going to get rid of that root 3 in the denominator. So the nice thing is radicals are the inverses of exponents. So the square root of 3 is the opposite of taking the square root or of squaring it. So what I can do is to get rid of that radical, I can square the square root of 3. Now, we can't square the bottom, square the top. It's not going to work like that. But what we can do is we can consider the square here as a repeated multiplication. This is root 3 multiplied by root 3. So what that means is I want to take this entire fraction and get rid of the square root in the denominator by multiplying it by a root 3 in the denominator. And what that'll do is the square root of 3 times the square root of 3 is the same thing as squaring the square root of 3. And when we square the square root of 3, we get 3. It gets rid of each other because they are inverse operations. But again, I want to make sure I'm multiplying this by something that is equivalent so I don't change its value. So if I'm going to multiply the square root of 3 in the denominator, I need to multiply the square root of 3 in the numerator as well. Okay, so this can be done relative ease when the denominator is a monomial like this one, but what happens when it is a binomial? So let's just finish this question and then take a look at how we deal with something that is a binomial. So what's going to happen here is our 5 times root 3 simply becomes 5 root 3. And then root 3 times root 3 is 3. So we get 2 times 3. Or 5 root 3 over 6. And that is our answer. So this fraction right here is in fact equal to the fraction we started with. They are equal to the same thing. And if you aren't convinced, grab a calculator and plug these two things and you'll get the same answer. But this one has a denominator that is a whole number or just not a radical, whereas this one has a denominator that is a radical. And that's what we're trying to do. We're trying to get radicals off the denominator and into the numerator. Okay, so that was with a monomial. So with a monomial, it's not too bad. All you need to do is just see, okay, well, I have a radical here. Let's multiply it by that same radical. They're going to cancel each other out and leave me with a whole number at the bottom. Great, done. With a binomial, it gets a little bit trickier. So with a binomial, what we need to do is we need to multiply by what's called the conjugate. So for a binomial denominator that contains a square root, multiply both the numerator and the denominator by a conjugate of the denominator. So what is a conjugate? A conjugate is two binomial factors whose product is the difference of two squares. So for example, a plus b and a minus b are considered conjugates because the difference of squares here is a squared minus b squared. So if you factored a squared minus b squared, we'd end up with these two factors, right? So we call these two things conjugates. And the reason this is useful is because you'll notice that if I take a plus b and I multiply it by a minus b, what ends up happening is I square a and I square b. So if I'm working with a radical, what will end up happening is if I take that radical and I square it, it's going to turn into a whole number. It's going to get rid of that radical. So that's going to be our plan here. So let's take a look at this example down here. 5 root 3 over 4 minus root 6. And again, I don't like this root 6 in my denominator, so let's rationalize it. So what we're going to do is we're going to multiply this fraction, or this denominator, by its conjugate. So again, the only thing that's different between a conjugate is if this is 4 minus root 6, the conjugate is 4 plus root 6. But again, just like with the previous question, I don't want to change its value, so I'm also going to multiply the top by 4 plus root 6. Okay, so now let's expand and simplify. So 4 minus root 6 and 4 plus root 6, those are conjugates. And what do we know about conjugates? When we multiply them, we get the difference of squares. So my new denominator is going to be 4 squared, which is 16, minus root 6 squared, which is 6. Now the top, on the other hand, we have to do a bit of calculations here. We have to take this 5 root 3 and multiply it into my numerator. So we're going to multiply it by 4 and multiply it by root 6. So 5 root 3 times 4 is 20 root 3. And 5 root 3 times 6 is uh, 5 root 18. So then what I'm left with is 20 root 3 plus 5 root 18 over 10. And again, the nice thing here is that we have a common factor of 5, so I can simplify this even further to say that this is 4 root 3 plus root 18 divided by 2. Okay. Now, we didn't necessarily have to do this multiplication. What we could do is we could just leave it as factored, right? So 5 root 3 onto 4 plus root 6. We could leave it like that. And then the bottom again becomes 16 minus 6, which is 10. And the nice thing there is that the 5 and the 10, again, will simplify. So it's root 3 times 4 plus root 6 over 2. So either way, we get the same answer. It just looks a little different. One is factored and the other is expanded. So here's a couple of example questions that need to be first rationalized. So we have to take the denominator and we have to rationalize it. The first two are monomials in the bottom. So all we need to do here is multiply by the radical to make it so that it's not a denominator that is also a radical. So we get this one, we'll multiply it by root 3 over root 3. So we don't change its value, but we do change what it looks like. Same thing for this one, it's a monomial. For these ones, we have to multiply by the conjugate. Now, the question here also says, identify the values of the variables for which the expression is a real number. So what I mean by that is, make sure you're not breaking rules. So again, what are the rules? We can't take an even root of a negative number. So for example, for this question, what is p not allowed to be? Well, in this case, p could be anything. It's allowed to be negative because we have a 3 here. If this was a 2 or a 4 or any other even number, p is not allowed to be negative because that would make the number underneath negative. But where it's a 3, there is no restriction on p. So for this one, p could be anything. But for question D here, where it's a square root, now we have an even number. We'd have to say that x is greater than or equal to 0, right? It has to be some positive number or 0. Okay, so go through these, give them a try. What you can do is if you want to see me do these questions, come to the live session on Thursday, and I can always try them then. Okay, but for now we're going to move on. So radical equations, that's what we are working towards right now. So the goal now is to not just work with radicals and simplify radicals, but now what we want to do is we want to solve radical equations with the intentions of someday working with radical functions, right? F of x equaling the square root of x, right? Graphing these things, learning about their properties, things like that, right? But we're just gonna stick with the radical equations for now, and someday we'll see these radical functions. But for now, let's just look at radical equations. So how do I solve a radical equation? So here's my equation that I want to figure out what is x and what value of x is going to make this thing work. Now, before we get started, I need you to really pay attention. The square root of x plus 5 is not the same thing as the square root of x plus the square root of 5, right? We just went over how this doesn't work like that. So make sure that you're not doing things like this. But the nice thing about that is if I gave you the square root of x plus the square root of 5 is equal to some value, you can't just take the square of both sides and find the answer that way because this is not x plus 5. It doesn't do that, right? We have to deal with each of these terms separately. But when we have a square root symbol over excuse me, over everything, then yeah, The square root of x plus 5 squared, that's your inverse operation, so those are going to cancel. Okay? So step one, when solving these radical equations, we want to isolate the radical on one side of my equation. So we want to make sure that wherever my radical is, it's by itself. Now, if you have two instances of radicals, you might not want to put them both on the same side. You might want to leave them on separate sides. And we'll take a look at that in a second. But if there's just one instance of a radical, get it on one side of your equation, get everything else on the other side. And then once it's isolated, we're going to square both sides. So for this question, where the x plus 5 underneath the radical was already isolated, I'm going to take the square of both sides. And again, the nice thing is when I take the square of a square root, those are inverse operations, so we're just left with x plus 5. Now, on my right-hand side, we're taking the square of a binomial, so this needs to get FOILed, right? X minus 1 squared is the same thing as x minus 1 times x minus 1. So when we do that multiplication, it's x times x, and then negative 1 times x, and x times negative 1, and negative 1 times negative 1. That's your FOIL, so make sure that you're not skipping that step. Okay, so now that I've taken the square of both sides, step 2.5 before we move on to step 3 is we have to make sure there are no more radicals. If there are any radicals left, we're going to go back up to step 1 and restart. So isolate it and square it, isolate and square it until we have no more radicals. Once all the radicals are removed, then we can move on to step 3 where we're going to solve for the remaining value of x. So here, this is just a quadratic. We're going to take the 5, move it over by subtracting it, take the x, move it over by subtracting it, and I get x squared minus 3x minus 4. And then that can be solved either using your quadratic formula, or you could graph it, or we could factor it, right? X minus 4, x plus 1. So then what are the answers here? We get a possible answer of x is 4 or x is negative 1. Great, two possible answers. So our last thing we have to look at once we have our possible answers, check. Just like with radical expressions, right, we had non-permissible values. We had answers that were not possible. The same thing is going to be true for these square root functions. We're going to have answers that aren't possible. And the reason that that happens is because we're squaring it in one of the steps. By squaring it, we're possibly creating roots that don't actually work, right? Because we can't take the square root of negative numbers. By squaring it, we're getting rid of that square root, so we're getting rid of the chance of having one of those rules that don't work. So what you need to do is you need to take both of these answers, plug them back into your original equation, and then check to make sure that it works. So if I plug in the x equals 4, right, back into my original equation, I get the square root of 4 plus 5 is equal to 4 minus 1, right? And then the square root of 9 is equal to 3, and then, okay, great, 9, 3 is in fact equal to 3. Perfect. Do the same thing for the negative 1. So negative 1 plus 5 is equal to, and then negative 1 minus 1, right? And then we get 4 is equal to negative 2. Okay, well, here's our issue. The square root of 4 is not equal to negative 2. The square root of 4 is equal to positive 2, and this is an extraneous root. And again, what ended up happening is because somewhere along the way we ended up squaring both sides, if I take negative 2 and I square it, and I take the square root of 4 and I square that, I do get a positive 4 on both sides, so they end up being equal to each other, right? So that's why we have to make sure we're checking these extraneous roots, are checking for extraneous roots, because some of these answers might not actually work if you take them and plug them back into your original equation. Okay, so let's try one together. So here we have the square root of z plus 5 is equal to the square root of 2z minus 1. So this is one of those examples I was talking about earlier where we have two instances of square roots. And when that happens, I generally don't want them to both be on the same side, because it's just going to make our lives a little bit messier if they are. What ends up making our lives a little easier is getting one square root of one side and getting the other square root on the other. Now that I have my square roots kind of by themselves, what we can do is move on to step 2 and square both sides. So we square the left-hand side, we square the right-hand side, and again, what ends up happening is because the square root and the square are inverse operations, I'm left with z plus 5 is going to be equal to 2z minus 1. Now it's just a matter of isolating my variable and solving for z. So if I move my z over to the right-hand side, I'm left with z. If I move my negative 1 over to the left-hand side, I get 6. So then z is equal to 6. So now what we should do is check to make sure that that's going to work, right? So I'm going to take that 6, plug it back into my original equation. So 6 plus 5 is equal to the square root of 2 times 6 minus 1. So 6 plus 5 is the square root of 11 is equal to 12 minus 1 is also the square root of 11. And since we get the same answer on both sides, we can be confident that z does in fact equal 6. Okay. Okay, so let's try example number 2 now. So this is one of those examples where we have radicals on both sides of our equation. And what we're going to want to do is we're going to want to keep our radicals separate. The reason we want to keep them separate is because you move them to the same side, it's going to make it a little bit messier when it comes time to take the square of both sides. So keep them separate, but what we can do is we can get our numbers all to the same side. So what I mean by that is on my left-hand side, I'm just going to be left with the square root of 5r minus 9 equals, on the right-hand side, I get the square root of r plus 4, but I can get rid of this negative 3 by adding it. So if I add it to here, I get plus 1. So now that they're both on opposite sides, but the one of my radicals is isolated, we're going to square both sides. So when I square the left-hand side, the square root of a square, it cancels. So I get 5r minus 9. And then when I square the right-hand side, this thing here under the square root sign is one term. So this whole bracket is considered a binomial. And when we square a binomial, a plus b squared, we get a squared plus 2ab plus b squared, right? Something we should hopefully be familiar with. That's our perfect square. So then what we can do is we can use that pattern in our advantage here. So the first term just gets squared. So the square of the square root of r plus 4 is r plus 4 plus 2 times a times b, or b in this case is 1, so times 1, just like that. And then plus b squared, or 1 squared, is 1. Okay, so now, because I'm left with an equation that still has a radical, I need to restart my process where I want to isolate that radical. So if I have 5r on the left-hand side and an r on the right-hand side, I'm going to subtract an r to move it over, and then negative 9 on the left-hand side, and 4 plus 1 is 5 on the right-hand side. So I'll subtract 5 from both sides and move that over, and I get 14 is equal to 2 times r plus 4, the square root of r plus 4. Now you could square both sides at this point, but it might be easier to divide both sides by 2 first. So we get 2r minus 7 is going to be equal to the square root of r plus 4. Right, so now what we want to do is square both sides. Now that we have our radical isolated again, we're going to square both sides once more. Right, so again, this is a binomial squared, so a squared is 4r squared, and then 2ab is negative 28r, and then b squared is plus 49 is equal to, and then the square of a square root cancels, so r plus 4. And now we're going to be left with a quadratic, which we can solve. So we're going to move everything to the left-hand side, so 4r squared minus, so if I have positive r and I bring it over, I get negative 29r, and then if I subtract 4 from both sides, I get plus 40. 5. So here, this thing is equal to 0. All right, the numbers are relatively large, so it can be a little tricky to tell if this is going to be factorable or not. So before you go through all the work of trying to figure out if it is factorable, what I suggest is just check the discriminant. All right, the discriminant is b squared minus 4ac. Right, so we'll just check the discriminant quick just to see what that gives us. So if we take negative 29 squared and we subtract 4 times 4 times 45, we get the discriminant is 121. And what that'll tell us is if our discriminant is a perfect square, which it is, 121 is 11 times 11, this thing will be factorable, right? So at this point, we could use our quadratic formula or we could factor it. Either way, we need to figure out what r is going to be. So if I wanted to factor it, we would do slide and divide. So take the 4 and multiply it by 45. So r squared minus 29r plus 180 is equal to 0. And then now we're looking for two numbers that add to give me negative 29 and multiply to give me 180. So we'd have to go through some kind of process to figure out what those numbers are. And what one thing I like to do is I like to look at 180 times 1 and then kind of manipulate both sides of this in order to get what my other factors could be. So 180 times 1. So if I take 180 divided by 2, I get 90. I take 1 and I multiply it by 2, I get 2. And then I notice here that 2 times 90 is equal to 180. So if I divide that by 10, I get 9. Multiply this by 10, I get 20. 20 times 9 is also 180, and 20 plus 9 is 29. So I get r minus 20, and r minus 9 is equal to 0. But we did slide and divide, so now that I've done this part, I have to go back and divide by the same thing I slid. So I get r minus 5, and 4r minus 9 is going to be equal to 0. So then my answers here are r is 5 or r is 9 over 4. Okay, so we have two possible answers here, but we don't necessarily have the final answer because one of them could be extraneous. So what we need to do is we need to go back and check our answers in our original equation. So we're going to take our original equation and we're going to use our two possible answers here and solve to make sure it's going to work. So let's do that. Let's take my r equals 5 and plug it into my original equation. So the square root of 5 times 5 minus 9 minus 3 is going to be equal to the square root of 5 plus 4 minus 2. So 5 times 5 is 25, and 25 minus 9 is 16. So this is the square root of 16 minus 3. And 5 plus 4 is 9, so the square root of 9 minus 2. So the square root of 16 is 4 minus 3, and the square root of 9 is 3, so 3 minus 2. So 4 minus 3 is 1, and 3 minus 2 is 1. So since I get an answer that makes sense, that means r plus 5 is in fact an answer for this question. All right, and now let's do the same thing for 9 over 4. So again, the square root of 5 times 9 over 4 minus 9, and then that minus 3 is going to be equal to the square root of 9 over 4 plus 4 minus 2. All right, go through the same process. So the square root of 45 over 4 minus 9 minus 3 is going to be equal to the square root of, so this is 16 over 4. So 16 plus 9 is 25 over 4 minus 2. Right? Some of you might not be comfortable with fractions, but I am going to work in fractions just because that's something we should be getting used to. So 9 is 36 over 4, so 36. 45 minus 36 is 9 over 4 minus 3 is equal to the square root of 25 over 4 minus 2. So the square root of 9 over 4 is 3 over 2 minus 3 is going to be equal to the square root of 25 over 4 is 5 over 2 minus 2. Okay. So this 3 over 2 minus 3. So 3 is 6 over 2. So it's 3 over 2 minus 6 over 2 is negative 3 over 2. And 2 is 4 over 4 over 2. So 5 over 2 minus 4 over 2 is positive 1 over 2. And what we find is that those are not equal, so this root is extraneous. So our only answer here is the r equals 5. And if you tried to use the 9 over 4, it doesn't work. And again, what ends up happening here is because we're squaring both sides, we end up making an answer that possibly couldn't work if we hadn't squared it. Okay, so one more question and then we'll call it a day. This one, both radicals are on the same side. And again, what I suggest doing is don't leave them on the same side. Because if you try to leave them on the same side, you're going to end up squaring both sides. You're going to end up squaring this side, and you're going to get x plus 19. Great, not bad. X minus 2. Again, not bad. But the middle part here is 2 times a times b. And you can see how much of a mess that is, right? Like, look at how ugly that thing is to work with. So again, what I suggest is isolate one of your radicals, not both. Don't leave them both on the same side. Just get one of them by itself, right? So pick one. It doesn't really matter which one you're getting by itself. Just pick one of them, get that one by itself, and then do your squares. So let's get the square root of x plus 19 by itself. So the square root of x plus 19 is going to be equal to 7 minus the square root of x minus 2. And now that it's by itself, we're going to square both sides. So we square the left-hand side, we square the right-hand side, and we get x plus 19 is equal to a squared, so 49, 2ab. So 2 times 7 is 14, and b is root x minus 2. And then b squared is x minus 2. Okay, isolate your radical again. So we get an x over here. We have an x over here, so they actually end up canceling. When I do 49 minus 2, I get 47. So if I bring the 47 over, I'm left with 28 is equal to 14 on 2 x minus 2. Divide both sides by 14, and I get 2 is equal to the square root of x minus 2. Now again, I isolated my radical, so now let's take the square of both sides. So 2 squared, that's easy enough, that's just 4. So 2 squared is 4. And the square root of x minus 2 squared is x minus 2. So now if I get x by itself, I add 2 to both sides, and I get x is equal to 6. So only one answer this time. Great, not too bad. But we still have to check to make sure that that answer isn't extraneous, right? Because if it is extraneous, then we have to deal with that. All right, so let's take that x equals 6 and plug it back into my original equation and make sure that it's going to work. And if it doesn't, it may be that this question didn't have an answer. There was no answer that's going to work. So let's check x equals 6. So the square root of 6 plus 9 plus the square root of 6 minus 2 equals 7, right? So 6 plus 9 is 25. No, it's not. 6 plus 19, sorry, 6 plus 19 is 25, and 6 minus 2 is 4, and the square root of 25 is 5, the square root of 4 is 2, and yes, 5 plus 2 does in fact equal 7. So since we get an equation that works, then we can be confident in our answer. Okay, and that's it. That's it for radical equations. So again, what I'll do is I will post this along with an assignment or a worksheet for you guys to try. I'll have a live session on Thursday, and hopefully I will see everybody there, and the quiz will be on Friday. I hope everyone had a great long weekend, and I will see you all on Thursday. Have a great day.